Hey, this is the first video related with the model development of a reinforced concrete beam using nonlinear analysis and nonlinear material properties. Some of the choices during the model development have been previously motivated during the course lectures. So, please, if you need some more clarification, refer to these lecture notes. Here, we are going to focus on motivating some of the input parameters and when are they important to modify within the main feature already selected or already taken. First, we are going to start using the model that we developed for the linear elastic with the reinforcement included. We open. Once the model is open, we need to follow the same steps as we did during the linear elastic model development to create the new materials, the new nonlinear materials. So if we go to the main menu in the tab model and then we choose the materials section, we are going to see the two materials that we already have, that are the linear elastic materials for both the concrete and the reinforcing steel. So if we then create a new material, we can go by model, materials and material, or just by clicking at this button, we open again the new material window. The first that we have to do here is change the material name as we did before. We rename it as concrete nonlinear, and then we need to choose the category. So as you remember, before we stick to the concrete design codes, but now as we want something more sophisticated with more personalization options, we are going to take the concrete and masonry. Here, if you go to the second comic box, we have many options for the concrete model. Which is the best option and with which one fits more to our model, it's going to depend to the different boundary conditions, the geometry, the materials, etc. If you are interested in detailed information of the different material models, you can click on the link to see another video specifically dedicated to this. But clicking at the OK button, we can go to the option to the personalization of the material. Then we have the first series of the choices that we can include in our material model. Right now we leave this like unchecked, but for the next task, some of you will need to play with these options. Then we need to fill the different material properties. First, the linear elastic material properties, modulus, Poisson ratio, and mass density. What we have, we can go to the total strain base crack model. Here we choose rotating 150 millimeters. Then here the tensile behavior, we need to check the material model. We are going to follow with Hordic, the tensile strength, 3 megapascals, and the energy fracture. These extra parameters are described in the same videos for the material model selection. So the compressive behavior, we're going to choose a nonlinear one based on Thorenfeld that mainly needs the compressive strength. We can choose 33 megapascals, for instance. These other personalization parameters also well described in the same video. So by clicking close, we have now our new nonlinear material concrete. Then we can continue by creating the nonlinear steel. Again, we click new material, we can name it following the same nomenclature, and then we go to reinforcement and pile foundations as the same as linear elastic, but here in the material model we will choose von Mises plasticity. Again, you will see different plasticity models, but the one that we consider adjusts better to the reinforcement or the steel reinforcement behavior is the von Mises plasticity. So linear elastic at the beginning and with plasticity based on the von Mises criteria. Again, we have some aspects to include, but as you remember, we can modify later on in the new window. The parameters that we need, as before, the modulus of elasticity for the linear elastic part, and then we have a new section that is von Mises plasticity. Here we have different options. If we consider hardening or we just consider perfect plasticity. That's again depending on your problem, depending on your requirements. If you expect really high deformations for steel, maybe you need to include the hardening effect. But if you don't expect that much elongation of the steel, you can just go for the non-hardening, that is the perfect plastic model after yielding. In that case, we need to define the yielding stress, and when we reach this stress capacity in the bar, we are going to develop deformation without increase the stress on the bar. So perfect plastic. If we close, we already finished with the creation of the materials. As we might expect cracking on our beam, we should consider the possibility to increase the integration points of the cross-section. Each beam element has 2 integration points, and each integration point is defined by different cross-sectional the integration points. So we should increase the cross-sectional integration points to have better discretization of all cross-section in the plane of the cross-section. To do that, we need to go to model and then add some element data. We can assign concrete, nonlinear, integration points. And then here we need to choose the parameter that we want to define or the data that we want to add into the assignation of the elements. In that case is Sinte, that means number of thickness integration points. We can go for 10, for example. And then when we click enter, we have in element data the new property to assign to the concrete elements. Before we can proceed with the meshing, we need to create the different loads combination. So we go to the main window in model tab, then we click at the loads section. Then we can see the different defined loads, the different load cases that we created. We activate them, we can see the graphical interpretation. And then here we have the geometry load combination. So by default, there are one load combination for each load case, but then if we go to the open load combination table button, we can access to the specific table where we can define our own specific load combinations. Here first we are going to apply the permanent load. Then we are going to create another case for the variable load. We are going to apply the full load. So this is going to be the coefficient by which we are going to multiply the defined load. Then we are going to increase the permanent load and the variable load up to the ultimate design loads using the specific coefficients. So when we apply this combination after the other two, we have the load up to the ultimate state limit level. And then for finish, we are going to create a new load combination where we are going to apply the load gradually up to double the ultimate load, and we are going to see which is the ultimate capacity of beam. We click close. We have now all the load combinations. Until here with the first video. In this video, we have seen first how to create the nonlinear material properties for concrete as well as for steel reinforcement. Then we increase the sectional integration points for the concrete cross-section. As we have nonlinear behavior now and we expect cracking, we need a better discretization of the cross-section. And then we define the different load combinations, which by means of which we are going to define or we're going to study the ultimate behavior of our beam. In the next video, we are going to see how to mesh our beam, then how to send the input parameters to the nonlinear analysis, and have some interpretation, some graphical interpretation of the obtained results. Thank you and see you soon.